Okay, good morning, gang. Welcome back. Today we're going to do a few things. We're going to start talking about section 5.1, which is on operations with functions. It's a very exciting section. I'm excited to cover it with you. Before I do that, I want to talk about one or two things relating to the exam. So I'm going to go ahead and turn on my screen share. Come over here. There was one question which was keyed incorrectly. So I've rescored that question, and I just wanted to make you guys aware. It might not be the one you were thinking though. So there's two here that I wanted to talk about. This one, the third multiple choice question, this one was originally keyed incorrectly. I just selected this as the correct one when this is in fact the correct. Of course, this being a negative lead coefficient and an odd degree polynomial, the graph should go up to the left and down to the right. So this second answer is the correct one, and originally this first answer was keyed as correct. So the majority of you actually got this right, but it was keyed incorrectly. So you'll notice a change to your score just this morning as I noticed that and fixed it. The other thing I wanted to talk about was a problem that a lot of folks got incorrect. And I want to come back to this, the second true-false question. So x cubed minus 2x plus 1 is an odd function. This is not true. This is neither even nor odd. And I want to talk for a second about why that's the case. So where is QCAM? There we go. First, let's get these introductory things out of the way. This is MAC1105. It's a lecture, and today is the 16th. So comments. Exam 2. First, MCQ, what was it, 3? Which would have been the 6th question altogether. Was keyed wrong. Fixed and regraded those. Negative x to the 5, what was it? Minus x to the 4 plus 2. So the end behavior of this thing, because it's an odd degree and a negative lead coefficient, it's going to look like this. Gotcha. All right. The other thing I wanted to talk about was I think it was question 2. Yeah, x cubed minus 2x plus 1. So this is TFQ2, which was question 2 overall. Function f of x equals x cubed minus 2x plus 1. It's neither even nor odd. And I think there might be a few things going on here about which you guys may be confused or uncertain, and I want to just take a second to clarify that. This is a polynomial, and the degree is odd, right? The dominant term here, the lead term, is this x cubed. So it is an odd degree polynomial, meaning the end behavior is going to be like this or flipped over. It's going to go up on one side and down on the other. However, that doesn't mean it's an odd function. Remember, an odd function is a function that has symmetry about the origin. So if you were to graph this function, and I guess let's do it in LaTeX because that's what you guys would have had during the test. If we graph this function, we can look for symmetry. And what we see is that this is not symmetric about the origin, right? This picture here does not have origin symmetry. If you reflect, for example, this point right here through the origin, you don't land back on the graph. Or if you were to take something up here and reflect it about the origin. If you were to shift this down 1 unit, that would have origin symmetry. But as it is right here, this is not symmetric about the origin, you see. Or this point, for example, up here, this is at like -1, 2, something like that. If you were to flip this through the origin, that would be at +1, -2 over here, but it's not. So this fella does not have origin symmetry. But there's something I think may have tricked you guys up when it came to this, and there's a shortcut. And I've cautioned about these shortcuts. You need to be very careful if you're going to use them. So the graph of f of x looks like what's exactly, yeah, so bounce here. Up and then down. About the origin. For example, this point, right? If we reflect it through the origin, we don't have a corresponding point over here. A little further down here. We don't have anything down there. So this is certainly not the graph of an odd function, but how do you square that fact with the shortcut that says if all the powers of x are even, then the function is even, and if all the powers of x are odd, the function is odd? Because here it appears to be the case that all the powers of x are odd. If you think back to the lecture where we mentioned that, there was a little caveat there, and that was that you can't have a constant term, right? In order for a function to be an odd function, you cannot have a constant term because this is really x to the 0, and 0 is even. So if we want to play that game, you can understand this in that context. So this power is odd. This power is odd. But this power is even. So that's how you can kind of see this in the context of that trick. So the all odd powers are all even powers trick that we described for polynomials. A polynomial is odd if and only if all the powers are odd. Polynomial is even if and only if all the powers are even. It does still work here, but it is a subtle thing. So the safe path, since you guys have graphing calculators during this test, and all of our tests, if you're trying to discern whether a function is even or odd, look at the graph, right? That will always tell you, and it'll tell you right away. It's a very low effort thing. So just throw this into your graphing calculator, take a look at the graph you get out, and that will let you know whether your function is even, odd, or neither. Since this certainly doesn't have y-axis symmetry, and it also doesn't have origin symmetry, we can be 100% sure that this function is neither even nor odd. But I agree, it is a subtle thing. And I just wanted to address those two questions with you. Are there any questions for me about these two exam problems? Okay, I think the larger catch, again, on the second one, on question 2, was that we're confusing an odd degree with an odd function. And just because you are an odd degree polynomial does not make you an odd function. Remember, for a polynomial to be odd, every power of x needs to be odd. And since this constant term is really an x to the 0, that is actually an even power. No, I have not put the grades into Pearson yet, so that's a good question. Brooke, no, the exam 1 grades are in Pearson. I put those in a long time ago, but I have not put the exam 2 grades into Pearson yet. I'll be doing that this afternoon. Kendra asks, why is this a degree 0 instead of a 1? So the constant term is a degree 0 term. If this was a degree 1 term, then this would be plus 1x, right? Or just plus x rather than a plus 1. Remember, x to the 0, anything to the 0 is 1. This is sort of an old-fashioned trick that we teach in 1033. But if you didn't take 1033 here, if you're jumping into this class from high school or elsewhere, you might not have remembered this. But certainly, yeah, anything to the 0 is 1. So one of the ways you can think about the constant term 1 is as 1 times x to the 0. If this was a 5, I could say this is 5 times x to the 0. So this is kind of a neat way to think of polynomials as descending powers of x. This is x cubed plus 0x squared minus 2x to the 1 plus 1x to the 0. It's a little sneaky. All right. I am considering doing something like the exam 1 reflections. You guys remember those, for an option to earn some bonus points on exam 2. But I'm going to have to clear that with the department chair. There's some issues with the DLP that I don't want to run into. Don't want to upset anybody in the department by doing something with the DLP that they don't want us to do. But I think a number of people would benefit from something like that. I think it's worth doing, both in terms of the actual reflection and what good that might do you, and in terms of the points. So I will see if I can do that. And if we are able to, then I'll do the exact same thing we did after exam 1. You can complete a reflection to earn up to 3% extra credit or points back on the test. But that is all I have to say about exam 2 for now. So I am going to transition now into the new material for this week. There are some new homeworks up for this week. There is a new quiz up for this week, and it's following the same schedule that we always do. It's releasing today. It will be due next Tuesday at the start of class. I think I forget the homework numbers. Let me see what the numbers were. It's like 14, 15 or something. Exponents, yeah, 14, 15, and quiz 5. Homework 14, homework 15, quiz 5. Open today. They're going to open at the end of class. They're not open yet, and will be due at the start of class next Thursday. You may recall from the beginning of the semester, I mentioned this class kind of has a difficulty spike, a difficulty plateau. We make a jump. We're approaching that jump here. So today's lecture is on homework 14. And this is all about operations with functions. The good news is that this section is, I don't think this section is that tough. I think most students actually find it a little bit boring. But mathematicians get really excited for this stuff because there's something very cool kind of just beneath the surface here. So I want to talk to you a little bit about that thing that's just beneath the surface. We're used to doing algebra with numbers, right? Every time you see a symbol like X or Y or A or B, it's understood that that symbol is like holding the placeholder for a number. So you know, if it's a variable, you're allowed to plug numbers in for it. If it's a constant, maybe it has one specific value, but they always represent numbers. Today, what we're really going to start doing is studying the algebra of functions. So it turns out you can, just like you can define algebra for numbers, right? Like x plus y or 1 over x minus 1 over 5y, just like you can do those sort of things, we manipulate symbolically symbols that represent numbers. You can also manipulate symbolically symbols that represent whole functions. And this is a big deal to mathematicians. We go on to study spaces of algebras of functions, and it's really, really cool stuff. But in order to get there, you need to learn the notation. And this homework 14, which is section 5.1, is really where we learn that notation. So this is, as it says, all about operations with functions, and I'm just going to dive right in here. So given two functions, f and g, and I'm leaving off the of x's here because it's nice to kind of learn to use a slightly more grown-up language where you refer to the function as f or g, and you refer to the output as f of x or g of x. We can form new functions according to the rules so here are the new functions I'm going to form. They'll be called f plus g, f minus g, f times g, f over g, and then the last one is kind of the exciting one, f circ g. Some people read this as fog, but this middle thing here is not the letter O, it's a little circle. And we can do this in the other direction, g circ f. The latter two are the fun ones, but in order to kind of build up to those, we're going to go through these. The function f plus g is defined by the rule that f plus g of x. So how do you define a function? I have to tell you what it does to every input. If you know what any given function does to every input, then you know what that function is. And the idea here is that we know the functions f and g. F and g are given to us. So I want to form this new function out of them. The way we do that is by saying, okay, well, f plus g of x, it's just f of x plus g of x. So if I want to know, like, what is f plus g, the function f plus g evaluated at x equals 5, then I take f of 5 and I add that to g of 5. The function f minus g is defined in the corresponding way. F minus g of anything is f of that thing minus g of that thing. So we're practicing our function notation. That's really what we're doing. And this is a skill that we need to develop. It is crucial. You can probably guess what I'm going to do with these next two. F times g. So if I want to define the function f times g, I got to say what it does to x. F times g of x. Well, that's going to be f of x times g of x. F over g. If I want to define what the function f over g does to an input x, it's pretty intuitive. The reason we make that notation what it is because it's evocative of what we're doing. That's going to be f of x over g of x. But then these latter two, these are fun. The circle operator here is called function composition. we're composing two functions. And in mathematics, what it means to compose two things is to shove one inside the other. So the function f circ g, what this does is it takes g of x and then plugs that in to f. I'm so sorry, I'm so sorry. Here, we should say it like this. We should say f circ g of x is what we get by taking g of x and plugging it into f. In other words, we have f of g of x. So you can read this circle here also as of. This is f of g, or f circ g. You'll hear me say circ a lot, but some people read that as of, f of g, because that's what we're doing. It's f of g of x. And similarly, g circ f is defined by the rule that g circ f of x is the composite operator done in the other direction. It's g of f of x. And it's really these bottom two operations that mathematicians get super excited about, because they're slightly weird operations when you compare them to the natural algebra things up here. But yeah, so these are how we define these new functions. So these are the names of each of the new functions: f plus g, f minus g, f times g, f over g, f of g, g of f. And these are how they're defined. In practice, what this is going to mean is you're going to be given the two functions. I'll give you a formula or a table or something like that, maybe a graph for each of the functions f and g. And you'll be asked to put together some information about the function f minus g, or some information about the function f over g, or some information about the function g of f. The bottom two operations are the really exciting ones when we're studying the algebra of functions. This is kind of like the function version of multiplication. It's not multiplication, right? This is multiplication. Here we're multiplying the two functions f and g. But if you want to study how functions interact with one another, it turns out that this is the cool one. I don't want to waste any time. I think it would be wise for us to just jump right in and look at some examples, and I'll take those examples from your homework. Oh, I can't do it here. God damn. That's fine. Let's take just a second. I want to refill my coffee. Okay. So express these symbolically. Oftentimes we want to find the domain also. So maybe, well, let's start with something fairly gentle. Let's take these two. Let's look at number 4. So I'll have f of x be 6x plus 1 and g of x be 3 over x. And we're going to find a bunch of things, right? I'll just, I won't do these exact ones. I'll make some stuff up, but Let's do F over G. 4 and F of G of 3. So one of the things students often ask me when it comes to this section is, how do I even get started, right? I know what these things are, but I don't know what to do. And the trick is to just trust the definition. Trust the definition and then follow your nose. So if I want to find F plus G of 3, if I want to find this, the trick is, and make sure you have these definitions in your notes. If you did not get these definitions in your notes, I'll come over here. You can take a screen capture or something, but it's really important you get these definitions nice and clear in your notes. You can screen cap those if you want. We're going to refer to them a lot today. Just trust the definition. So if I want to find F plus G of 3, I need to start with the definition of F plus G of X. F plus G of anything, remember X is just a symbol that stands for a number. Here 3 is the number that I've plugged in for X. This should be F of that thing plus G of that thing. So F plus G of 3 is F of 3 plus G of 3. And now it's kind of like one of those problems from the very first homework. I just have to figure out what each of these little pieces is and then do the operation between them. So F of 3, that's what I get by plugging 3 in for X here. So that's 6 times 3 plus 1. That's 18 plus 1 is 19. So F of 3 is 19. And G of 3 is 3 over 3, which is 1. So this is 20. We can maybe up here if we want F of 3, this is 6 times 3 plus 1. G of 3 is 3 over 3, if you want to think about where each of those is coming from. So this new function, F plus G, if we evaluate it at the input 3, we get out 20. In other words, if I was looking at the graph of F plus G as its own function, the ordered pair 3, 20 would be on the graph. Is everybody comfy with this first one? Are there any questions about where any of the pieces came from or why we're writing things like this? Oh, this thing's covering up the chat. Let me move this out of the way. Okay. All right, if not, then we're going to look at F times G of 1. Again, just trusting the definition, this would be F of 1 times G of 1. So I need to figure out what is F of 1, what is G of 1. F of 1 is what I get if I plug 1 in here. That's 6 times 1 plus 1. That's 6 plus 1 is 7. So this is 7 times G of 1 is 3 over 1. Well, that 3 over 1 is 3. 7 times 3 is 21. I promise I'm not doing anything clever here. The next one isn't likely to be 22. It just worked out that way. But yeah, we just follow the definition. So F times G of anything is F of that thing times G of that thing. Here the thing is 1. So F times G of 1 is F of 1 times G of 1. F of 1, this piece is 7, because when you plug 1 into F of X, you get 7 out. G of 1 is 3, because when you plug 1 into G of X, you get 3 over 1, which is 3. Let's try the next one, F over G of 4. This should be F of 4 over G of 4. That's the definition. So what is F of 4? F of 4 is 6 times 4 plus 1. 6 times 4 is 24. 24 plus 1 is 25. So the top here is 25. And then downstairs, I have G of 4. Well, what is G of 4? If I plug 4 in for this, I get 3 over 4. And I'm going to put that in parentheses. That parentheses is very important. So upstairs, f of 4 is 25. Downstairs, g of 4 is 3/4. If you don't write the parentheses downstairs, this fraction is ambiguous. You really want to write this piece in parens because you've got a little fraction within a fraction. Remember, fractions always have their top and bottoms like in parens. Just don't write them like that because the fraction bar implies the parentheses. But here you really want to write them because it's going to tell us how to simplify this. I have Calc 2 students who still struggle with this. So nip this in the bud now. Get good with fractions here in college algebra, and you'll have a much easier time in calculus. How do you simplify 25 divided by 3/4?
You multiply 25 by the reciprocal of 3/4.
Yeah, very good. We're going to multiply the top by the reciprocal of the bottom. So this would be 25 times 4/3. 25 isn't divisible by 3, so there's not going to be any simplification we can do here. But 25 times 4 is 100. So this is 100/3. Any questions about how we found this or simplified it? Brookman asks an interesting question. Can we write this as 33.3? Well, if you want it as a decimal, it's really 33.3333, on and on forever. So if you want to write that like on paper, this is the notation that I'm most familiar with, putting a little bar over the 3 after the decimal place to indicate that that repeats forever and ever. But this, I think, is much nicer, right? For starters, you can't really type this. You could round this to any particular decimal place you wanted and type that, but because it goes on and on forever, there's no nice way to type that either. So the fraction is genuinely the preferred answer here. This is exact, it's clear. If you were to round this at any particular decimal place, like 33.3, if we were to cut it off here, that's actually not quite correct. I'll show you what I mean. If we take 33.3 and we multiply by 3, we don't actually get 100, we get 99.9. And we can, if you round somewhere else, you'll get something closer to 100, but still not exactly 100. So this is actually the preferred notation. Yeah, precisely, Mark. Yeah, 33.3 is a reasonable and valid estimate, but it's not 100% accurate. So I would prefer the fraction. If you're going to write out the decimal, that's fine, but be clear that you're rounding. You could say, 33.3 when rounded to 1 decimal place, and that would be okay. But make sure you look carefully at the question you're trying to answer and see whether it gives you permission to round. If it doesn't give you permission to round, then I would very much like you to write it as a fraction. And Pearson would probably count it as wrong unless they gave you permission to round. All right, let's move on to this last guy down here. This is a fun one. So again, people ask, how do I get started on these? And usually they don't ask that about these first few ones. Usually they ask that about this guy. But the answer is always the same. Trust the definition. So what is the definition of f circ g of 3? Well, if you look back at your definition page, f circ g of x is f of g of x. So f circ g of 3 should be f of g of 3. And then we need to be careful about the notation here too. So the parentheses, the big parentheses on the outside, these are important. The little parentheses on the inside are important. It's not describing anything to do with multiplication. I want to be very clear about this. This is not f times g of 3. It's not f times g times 3. It's not anything like that. Here, these parentheses denote plugging into a function. And that's one of the first conceptual hurdles we need to cross. So if it's something in your head that you've been reading as times, even if you're doing the problems correct, in your head, when you see this stuff, if you've been saying times, try to fix that. Try to start saying in your head f of this rather than f times this, because it is not multiplication. And if you fix that in your head now, it will make things easier for you later. To simplify from here, we work from the inside out. What is g of 3? Well, that's not bad. I figured that out up here, remember? G of 3 is 1. It's 3 over 3. G of 3 is what you get when you plug 3 into this function. So f of g of 3 is f of 1. Because the inside thing here, g of 3, is 1. We can even say this down here. Because g of 3, the inside, is 1. And then f of 1, I've computed that also today. F of 1 is 6 times 1 plus 1. That's 6 plus 1, that's 7. So f of g of 3 is 7. Questions on this guy? Okay, if you don't have questions for me, I have a fun question for you. Many of the operations we study in mathematics are commutative, right? Like 2 times 7 is the same as 7 times 2. Multiplication is commutative, addition is commutative, division is actually not commutative, meaning if you swap the numbers around in a fraction, you don't get the same thing. But what about function composition? Do we expect g of f of 3 to be the same as f of g of 3?
No.
Yeah, in general, function composition is not commutative, meaning when you change the order, we expect things to not necessarily stay the same. Let's see what we get. This would be g of f of 3 like this. And then f of 3, remember that that's 19. That's 6 times 3 plus 1. We used that earlier. So this is g of 19. And g of 19 is 3 over 19 because g of anything is 3 over that thing. And 7 is not 3 over 19, right? 3 over 19 is smaller than 1. It's way smaller than 1. It's a little bit bigger than 1, or sorry, a little bit smaller than 1/6. 7 is much, much larger. So our first sort of note here, the f circ g of 3 is not equal to g circ f of 3. And in general, the operation of composition is not commutative. So it's nice when our operations are commutative. I don't know why my pen doesn't want to write on this part of the page. It's fighting me over here. We like when our operations are commutative, but this is one case where it's not. Composition is associative, it turns out. Associative, remember, means that if you've got like 3 things, you know, F, circ G, circ H, the order you do them in matters, but you can like work from the inside out or work from the outside in. Either way is okay. All right. Any questions on what we did here? These things. So we can figure out what f plus g looks like one number at a time by saying what is f plus g of 3, what is f plus g of pi, what is f plus g of 12, or f plus g of 115. But sometimes we also want to find a formula for these functions. So the next problem I'd like to do is going to be finding a symbolic formula for each of these in some context. So let's look at, let's look at symbolically. Sure, why not? 3x. Do something a little more interesting if we can. All right, yeah, we'll make it simple. How about, I got. And I'm not going to run through all of these here, but we'll do like f minus g of x, maybe f times g of x. We can do, how about g over f of x and f of g. So instead of looking one number at a time, I just want to find an algebra expression for each of these. I'm going to find a formula for each of these guys. And then if I wanted to, I could plug numbers into that formula to solve problems like the last one. So this guy's going to give us a new way to approach the problems like we just did. We can find a formula for each of these functions, and then you could plug whatever you wanted. Or you could try to graph them, or you could do any of the other things that we do once we have a formula for a function. Again, you just follow the definition. This should be f of x minus g of x. The only thing you need to do is remember to treat each of these things as chunks in their own right. Meaning when you add, subtract, multiply, or divide them, when you replace g of x by 4 minus x squared, or replace f of x by 2x plus 1, you need to do so in parentheses. So this is like 2x plus 1, parentheses, minus 4 minus x squared in parentheses. This is going to be, here, this 2x plus 1, there's nothing multiplying it out front. There's no minus signs or anything. So he's just going to stay 2x plus 1. But here I need to distribute this minus. And that's why I wanted to do this one, to emphasize that you really do need to write these things in parentheses. Because without distributing this minus, the answer would be wrong. So this is going to be minus 4 plus x squared. And then we can combine our like terms. I have an x squared, so I'll write that out front. I've got a plus 2x, right, a positive 2x. And then positive 1 minus 4 is minus 3. Questions on how we arrive at this? It's nothing too hard. Just make sure when you get started that you write the expressions that you're replacing f and g by in parentheses to make sure that you do whatever distribution or things like that is necessary. This next guy is also going to require some careful work. So f times g of x, this is f of x times g of x. That's the definition. We always start there. And now I'm just going to plug in what is f of x. The thing is, we make sure to plug in parentheses. So f of x is 2x plus 1. So I'll have parentheses 2x plus 1 times parentheses 4 minus x squared. And here we need to FOIL. So I'll have 2x times 4. That's 8x. And then my outers are 2x times negative x squared. That's minus 2x cubed. My inners are 1 times 4, so that's plus 4. And my lests are 1 times negative x squared, so that's minus x squared. And like the previous guy, we can rewrite this in standard form with the dominant term up front. So this would be minus 2x cubed, and then minus x squared plus 8x and minus 4. So careful use of parentheses are your friend. G over f of x, the next fella. This is g of x over f of x. And there's not much we can hope to do here. This is going to be 4 minus x squared divided by 2x plus 1. And there are no common factors top to bottom here. There's nothing we can cancel. Can't cancel the x because there isn't a factor of x downstairs to factor out, and there isn't a factor of x upstairs. So there's nothing more we can really do here. Remember, the fraction bar implies parentheses, so we could write these in parens if we wanted, top and bottom. That would be correct. But it's a little bit unnecessary because the fraction bar implies those parentheses. But if you want to, if you're being very careful, it's not a bad idea to write it like this, just to remind yourself. But the fun one is this guy. So remember the definition, f of g of x, or fog of x, is what you get by plugging g of x into f. And then from here, you've got a couple of ways you can think about it. We can say, okay, what's the inside? Well, I know g of x is 4 minus x squared. So this is f of 4 minus x squared. And here's where you have to be very careful. Remember, I said this is not multiplication. This is not f of 4 minus f of x squared. That is not correct. What we need to do is look and see if I plug 4 minus x squared into the formula for f of x, what do I get? That would be 2 times 4 minus x squared. And I'm putting it in parentheses, plus 1. Take a second and make sure you're really comfortable with where this is coming from. I'll say note. F of 4 minus x squared is not f of 4 minus f of x squared. This does not work. This sort of shit never works. That's a little bitty lie. That sort of shit works if and only if f is a certain kind of function. But I don't want to confuse you, and it definitely isn't true in general. So it just function notation doesn't work like that. Now we can clean up what we have over here. This piece, we can distribute the 2. So this, if I distribute my 2 here, I'll have 8 minus 2x squared, and then I still have this plus 1. And I could rewrite that in standard form as negative 2x squared, and then 8 plus 1 is 9. Questions on any of these? Okay. So you'll see a handful of problems like this where you're asked to evaluate some things based on those bits. But I don't think you'll have a terribly hard time with any of that, nor will you have a hard time with these tables. You're doing the same sort of thing here. So to look at, if we look here at problem 5, they want you to figure out like f plus g of 4. Well, you start by writing that as f of 4 plus g of 4. Always on these problems, no matter how the function is described, start with the definition. So f minus g of 1, that's f of 1 minus g of 1. Yeah, Kendra, I could show you something like that. But then I do want to go on to some of these that use the graphs. So just for fun. Let's say find and simplify f over g of x, where f of x is x squared minus 1. Oh, come on, pen. And g of x is x plus 1. All right. So here, f over g of x should be f of x over g of x. That's how we always get started. Just write down the definition. Now f of x is x squared minus 1, and g of x is x plus 1. And remember, we can think of these as being in parentheses like this. The top here actually factors, right? The top here factors nicely. And it does have a factor in common with the bottom. That top can be factored as x minus 1 times x plus 1. And the bottom is x plus 1. So you can cancel the x plus 1s. And you get x minus 1. I don't know why it's doing this always on that side of the page. X minus 1 over 1, right? Because this bottom is x plus 1 times 1. So here you just get x minus 1. Just remember, the trick to simplifying fractions, canceling, is to factor. You can only ever cancel common factors. So if your immediate step before was not factoring, you cannot cancel. But if you do factor and you find a common factor top to bottom, then you can cancel. Is there anything else we'd like to look at more closely here? We're all feeling Gucci comfy? I'd like to look at an example of a problem or two, maybe just one, where we're using graphs of functions to sort out some information about a composite. These can be a little bit tricky. So let me come down here. Let me see if I can't blow this up a little bit for you. No, not from the print dialog. Okay. So I'll copy this graph down. Or maybe a similar one here. Let's see what we can do. I'm going to say use the graphs. To find the following. I'll for you over here a couple of graphs. I'll make mine slightly different. Aren't robbed of the experience of solving that problem. So we'll call this one f of x. And just to be clear, there's some points that are on here. I'll call this 1, 1. And -1, 1. This, of course, would be 0, 0. I'm going to say over here we've got 2, 4, -2. I'll put the graph of f of x in purple like that. And the graph of g of x, let me put this in pencil. Let's do g of x like this. We'll just play around. Like so, and we'll say this is like -2, -4 over here on this guy. We'll call this pencil 1, g of x. Okay. So let's find, if we can, f plus g of 1. And how about g over f of -1? And how's about, let's say, see if we want to get up to bed. We need something like f of g of -1. Let's start with these. I'll label these A, B, and C, and then we'll come down into the space to the side to figure this out. So how should I get started with part A? How do I get started on any problem like this? Does anybody have a suggestion?
By finding where it hits 1.
Even before that, that's not a bad idea, but even before that, I'd like to come back just a little step further. So if I want to get started on part A, and I'm trying to hammer home a point here, so I apologize if this is. Seems a little bit redundant. So even outside the context of this particular problem where we're using a graph, how would we get started on sorting anything like this out? What have we been saying at the start of each of these examples?
Write out the definition.
Very good. So this is f of 1 plus g of 1. We always got to start here. And now, if we want to find f plus g of 1, we've simplified that to saying, okay, I want to find f of 1, and I want to find g of 1, and then I'm going to add those up. So we've kind of reduced this problem into two simpler problems. So now what is f of 1? Yeah, f of 1, we're looking along the graph of f of x when x is equal to 1. This is my x-axis. So when x is equal to 1, f of x, this parabola, his y value up here is 1. So f of 1 is 1. Plus, what about g of 1? If I look along the graph of g of x here, when x is equal to 1, g of x is equal to -2. So g of 1 is -2. And I might write this in parentheses just so we don't get confused about the operations. So remember, g is the pencil graph over here. And when x is equal to 1, g of x, the point that's on the graph there, is this guy. And that y value is -2. So g of 1 is -2. And then if I add 1 plus -2, I get -1. Is everybody comfy with what happened here? Okay, let's look at part B. Here I want g over f of -1. So again, I begin with the definition, right? If you're stuck on how to get started here, if you find yourself running into trouble, check and ask yourself, am I starting with the definition? Because as silly as it might seem, this really is the key to getting these right. Start by writing this as g of -1 over f of -1. And now we're just evaluating functions from graphs. It's just like in that first homework set. So g of -1, if we look along the graph of g of x, which is the pencil graph, we come over here to where x is -1. G of -1 is +2. And f of -1, if we look along the purple graph, when x is -1, f of -1 is +1. So this is 2 over 1, which is 2. And then part C, this is the fun operation, fog or f of g of -1. Circ g of -1 like this. We begin with the definition. This is f of g of -1. And just like the previous guys, we kind of want to work from the inside out. I can't tell you what f of this thing is without knowing what the inside of f is, like f of what? F of g of -1. Okay, well, you need to tell me what g of -1 is first. G of -1, this inside piece, I look along the graph for g of g. When x is -1, g of x is 2. So g of -1 is 2, which means that f of g of -1 is f of 2. And then f of 2, I look along the graph of f. when x is equal to 2, f of x is equal to 4. So f of 2 is 4. Questions on this fellow? Any parts? All right, this is pretty much everything you guys need to work through this homework set. Let me see here. Did that go away? Oh, damn, it did, didn't it? Yeah, maybe I closed it. We can pop this back up. I don't think there's anything else in this particular homework that you are unprepared to answer at this point. I'm going to just make a quick survey here. Evaluate each of these as well as some sort of thing. Finding its domain, right? So the domain stuff is a little bit more challenging. So I'd like to look at one of these where we play around with domains, and then I will let you guys go. Make sure there's not anything on this one. No, all right. So I want to talk a little bit about domains, finding domains algebraically. It's something that we've done. I just want to remind you sort of the basics here. This is something we talked about way back in the first week of class, but I think now that you've got some more experience solving these problems, it's worthwhile to revisit it before we look at the next example. What we want to watch out for, what I call red flags. And the shitty joke I usually say here is if you're on a date with somebody, like, you know, you go out with a guy and he tells you he hates his mom, that's a red flag. You need to watch the fuck out. So domain functions have red flags also. The big ones we need to look for here are any variables downstairs in a fraction. And the thing you need to make sure of is the bottom of a fraction can't be 0. So any numbers that make the bottom of a fraction 0, we have to kick those out of the domain. Other domain red flags, if you have any variable stuff under an even root, like under a square root or a 4th root or a 6th root, etc. The inside of even roots need to be greater than or equal to 0. There is a third big red flag here that I'm going to add after we talk about logarithms, but we're not there yet. So for now, these are the domain red flags we need to be aware of. So with this in mind, let's take a look at let's look at the function f over g of x, where f of x is the square root of x minus 1, and g of x is, let's go back to our buddy 4 minus x squared. root, R-O-O-T. Yeah, root is the R word here. So variables under an even root, that's a red flag. If you see something like x minus 1 underneath an even root, like we have here, we got some variable stuff hanging out underneath a square root. That means that we need to be careful. We need to look out for that red flag. So first, f over g of x, like this, the function f over g, is by definition f of x over g of x. And now I can just plug in each of these pieces. F of x is the square root of x minus 1. And g of x, that's 4 minus x squared. Hello? Hello, yes. Oh my God. All right. So from here, if we want to find the domain, we got to watch out for these red flags. There's 2 red flags here. All right, I'll stop here. This is fine. We have found f over g of x. But now for the domain, what sort of red flags do we see? Well, I've got some variables downstairs. I know the bottom can't be equal to 0. So let's figure out what makes the bottom 0. The bottom equals 0 if and only if 4 minus x squared equals 0. And that's the same as saying that 4 is equal to x squared. I just added the x squared to both sides. And then taking square roots, I see that's the same as plus and minus 2 being equal to x. So since my bottom is 0, if x is plus or minus 2, I know x is not allowed to be either of those. In addition to that, right, so this is 1. In addition to that, I know the inside of the square root has to be greater than or equal to 0. So here the inside will be greater than or equal to 0. Well, what do I have inside my square root? The inside of my square root is x minus 1. So here I need x minus 1 to be greater than or equal to 0. And I can add a 1 to both sides of that inequality, and I get x is greater than or equal to 1. So these are the things I need to be on the lookout for. I need to make sure that x is greater than or equal to 1, and also not equal to 2 or negative 2. Now, one of the things I noticed we had a little bit of trouble with on the test is taking information like this and putting it into interval notation. Maybe it's something we just hadn't practiced in a while. We had an activity on that way back in the day. But let's draw this domain on the number line. So maybe negative 2 is way over here. Maybe 0 is here. Maybe 1 is here. And maybe 2 is here. All right. I need x to be greater than or equal to 1. That means I've got to be coming from this set over here. I'm not interested in anything over there. I'm allowed to be equal to 1. That's good. I'm allowed to be anything that's greater than or equal to 1. So this whole side over here is looking pretty good. The only catch is I'm not allowed to be equal to 2, right? Because that's one of my numbers that I have to get rid of. I also have to get rid of -2, but -2 isn't in this set, so I'm not interested. I don't even give a shit about that. So my domain is everything from -1 up to 2, not including 2, and then everything from 2 all the way off to infinity. So the domain here is in interval notation, -1 to 2, union with 2 to infinity. One of the questions on exam 2 that a lot of people struggled with was the domain of that rational function, right? The multiple choice question. If you're at all uncertain what a set of real numbers might look like what does it look like if I kick out plus and minus 2 and I have to be greater than or equal to 1? Draw the thing on the number line, shade your set. I promise you it will help. Are we all comfy with why these two things look like this on the number line? Oh, it is. I'm so sorry. It is. Yeah. Yes, that is a 1. I don't know why I wrote down a -1. Yeah, this is a 1, right? This is a 1. I don't know what I wrote. I'm so sorry. Yeah, so the shaded set here is the set I'm writing down here. I think I was just looking at this negative. But yeah, this is a +1 right here. So this is a +1 right here. If I only had the square root, then I would say all the stuff greater than or equal to 1. And it would just be bracket 1 to infinity. But in addition to the square, I have this thing downstairs. So I got to make sure that that thing is not 0. So on the one hand, I have to be larger than or equal to 1. That means that I'm looking just at this stuff. On the other hand, I'm not allowed to be equal to plus or minus 2. So I need to kick out the 2. And if -2 was a possibility, I would need to kick it out also. But since it's to the left of 1, I'm not interested in it anyway. And then once we have this shaded, I can say, okay, so that's bracket 1 to 2 parentheses, union with parentheses 2 to infinity. All right, this is where I'm going to go ahead and end the lesson. I think we're almost exactly out of time. Please do get started on this homework right away. It's a little bit tricky, but it's not impossible. I think you'll find the first few problems maybe even boring. But be disciplined as you solve them, right? As you solve those first few problems, make sure you're writing down the definition. That will get you into the habits that you need to be in as you come to these harder problems. When you get to a problem like this, you really don't want to be in doubt about what this thing is. You want to be 100% certain and 100% comfortable, because you then have to go off and do this work, which is a little bit more complicated. And as always, remember your red flags. Watch out for those things. They're dangerous. All right, is there anything that you guys would like to ask about this before I let you go? Alrighty then, I do have an office hour today from 11 to 12. I'll be moving over to that right now. If you want to talk a little bit more about any particular thing, your test should be graded unless you took a makeup test or took the test in a different place or a different time. Then those I'm still getting to, but all the other tests have been graded. I do apologize for the miskey on question 3. That has been, or sorry, multiple choice 3, question 6. That has been fixed. And if you want to talk about anything else, come by my office hours. Otherwise, I'll see you guys on Thursday. Take care.